Very good morning, students. Today we are going to see Unit 5 Acoustics. Now this will be a very interesting physics lesson. Now here we are going to see how is the sound produced and transmitted. We are going to relate the speed of the sound frequency and its wavelength, and factors affecting the speed of the sound of the gaseous medium, demonstrating the phenomena of reflection of the sound, and we are going to determine the speed of the sound using the method of an echo. So we are going to Good morning, students. Welcome to science session. Today we are going to see an interesting physics lesson, that is Unit 5 Acoustics. Now in this lesson we'll be learning about how a sound produced and how it is transmitted, the relationship between the speed of the sound, frequency and the wavelength. Now what is the difference between the sound and the light waves, the factors affecting the velocity of the sound, and we'll be learning about the reflection of the sound, and in that particularly the reflection at the boundary of a denser medium and the rarer medium, even the reflection of the sound in the plane and the curved surfaces. Now in the next session we'll be learning about the echoes and the Doppler effect. Now let's go into the session, children. Now sound plays a very important role in our life, children, isn't it? We communicate with one another through sound, isn't it? So in our life we hear various varieties of sound, like animals, humans, horns, vehicles, birds, etc. Now sound becomes very inevitable, and we also have to understand how is the sound produced and how it is propagated, and how could you hear the sound from the various sources, isn't it? Now what is this acoustic means? So acoustic is the branch of physics that deals with the production, transmission, reception, control and effects of sound. So these are the things that is related to the sound. How is the sound produced? Now how it is transmitted, how it is received, and what is the control and the effects of the sound. So these are nothing but the acoustics. Sound, we have learnt about the properties of the sound in 9th standard, isn't it? Now we have also learnt about what is echo, isn't it? Now if you see, basically we have to understand how is the sound produced and how the sound reaches our ears from the various sources. What is sound, whether it is a force or an energy. So these are the basic things that we have to learn, isn't it? Now we are going to learn all these in this lesson. Now if you hear an ringing of bell, now you can conclude that the sound is produced by vibrations, isn't it? Now if a bell rings, in the sense ringing, in the sense it produces some vibration. This vibrating bodies produces the energy in the form of waves. So this is nothing but sound. So sound is transmitted in the form of waves. Now if it is transmitted in the form of waves, now can you hear the sound in vacuum? No, you cannot hear the sound in vacuum. So it needs a medium for the sound waves to transmit and to reach our ears. So the vibrating particles takes place. Now where these particles are present? These particles are present in the medium like air, water, steel, etc. So it needs a medium for its propagation. So sound can propagate through gaseous medium or the liquid medium or the solid medium, right? So even if you place an ringing bell inside a tub containing water, no, you could hear the sound, isn't it? So the medium, liquid medium, transmits the sound. Now what type of the wave is the sound wave? Sound wave is a longitudinal wave. Now I'll show you what is longitudinal wave. So sound waves are longitudinal waves, and that can travel through any medium, whether it is a solid, liquid or a gas. It can travel with a speed, and that also depends upon the properties of the medium, right? So what properties does the solid possess, or the liquid possess, or the gases possess? Depending upon that, the speed of the sound differs. So when it is traveling through a medium, what will happen? We said that the particles in the medium vibrate, isn't it, along the direction of propagation, isn't it? So there will be an movement in the particles, right? So there will be a displacement in the particles. So this displacement involves the longitudinal displacement, right? So this particles vibrates from its position. So as it vibrates, it produces a longitudinal movement. It moves forward, right? So due to the vibration, Now what will happen? It results in a series of high pressure and a low pressure, isn't it? Now for example, if the particle present here is vibrating, it starts moving, isn't it? So some of the particles move from here to here, isn't it? So here the particles becomes crowded in this place, isn't it? So it results in the high pressure region and the low pressure region, right? Now this high pressure region is called as the compression, right? Here the pressure is more, the particles are more crowded, so it is called as compression. And the less pressure region, which is relaxed, right, the number of particles in the medium is less, it is called as the rarefaction. So this is about the longitudinal waves. So you get a series of the compression and rarefaction, alternative compression and rarefaction regions are present, and this type of waves is called as the longitudinal waves. Now even this longitudinal waves can be represented like this. Now here you can draw lines with minimum distance between them, and here you can draw a crowded line, and again here you can draw the line with a minimum space, then again the crowded line. So this is the rarefaction region, and this is the compression region. So this is how you can differentiate between the compression and rarefaction. Now let's see the categories of the sound waves, that how it is classified based on their frequency. So now we have learned about what is frequency and what is wavelength in 9th standard, isn't it? Now what is wavelength, what is time period, what is frequency, what are the units for these terminologies, all these we have learned in the sound lesson in 9th standard, isn't it? So this is the classification of the sound based on their frequency. Now the first one is the audible waves. Now what is audible wave? Now if the frequency range is between 20 Hertz to 20,000 Hertz, then it comes under the audible range. Audible in the sense we are able to hear it, isn't it? Now for example, the vocal cords, that is your singing, isn't it? The singing voice, the stretched strings, right? So it produces a voice, isn't it? So these are the vibrating bodies that produces the sound, and that sound will be between the frequency 20 Hertz to 20,000 Hertz, and this comes under the class audible waves. The next one is the infrasonic rays. Now what is infrasonic rays? Now here the frequency will be below 20 Hertz, right? Now if the frequency is below 20 Hertz, now human beings cannot hear the sound. The waves produced by the earthquake, ocean waves, so all these are called as the infrasonic waves, which is below 20 Hertz. So we cannot recognize, or we are not able to hear those voices. Our human ears cannot recognize, or it is not audible to the human ears. Now the next one is the ultrasonic waves. Now what is ultrasonic waves? If the sound waves have the frequency greater than 20 Hertz. Now if it is greater than 20 Hertz, then it comes under the classification ultrasonic sounds. Now human ears again cannot detect these sounds, or it is not audible to the human ears, and these waves are produced by certain creatures like mosquitoes, dogs, bats, etc., dolphins, etc. So these are produced by the bats also. So these are called as ultrasonic waves. And now the next one is the difference between the sound waves and the light waves. Now sound requires a medium, because it requires a medium. In vacuum we cannot hear the sound. Now you would have learned an experiment in the lower classes, that you take a ringing bell and place it inside a jar which is vacuumed, or which is evacuated, in the sense the air is pumped out from the jar, right, which is vacuumed, right? And if you if the bell rings, you are not able to hear the voice, because it requires a medium, because the particles in the medium vibrate and it transmits the sound waves. But if you see, the light do not require any medium, it can travel even through vacuum. Now if you see the sound waves are longitudinal waves, while the light waves are transverse waves, where you have the crust and alternative troughs, right? And if you see the wavelength, the range, it is 1.6 centimeter to 1.65 meter. Now here the wavelength range is 4 into 10 to the power of minus 7 meters to 7 into 10 to the power of minus 7 meters. Now, the sound waves that travels in the air is about 340 meter per second, and this we know it very well, isn't it? The speed of this light in air is 3 into 10 to the power of 8 meter per second. So this is the difference between the sound waves and the light waves, and this is a very, very important question. So here we are going to talk about the velocity of the sound waves. Now when we talk about the velocity of the sound waves particularly, there are two velocities. One is the particle velocity and the wave velocity. Now why there are two velocities? Because the vibration of the particles makes the more propagate or transmit the sound waves. So there are two velocities. The first one is the particle velocity. The velocity of the particle in the medium is vibrating in order to transfer the energy, isn't it? So it is called as the particle energy. So it needs the velocity to move from one position to the other, isn't it? So in the form of vibration, now what will happen? The energy is observed in the form of vibration, it moves, it makes a displacement, isn't it? So the velocity of the particle that vibrates, that is called as the particle velocity. Now what is the wave velocity? Now the wave moves, right? The particles together as a wave moves through the medium, isn't it? So it is called as the wave velocity. Now we know the formula for the velocity, isn't it? Velocity is equal to distance divided by time. Now here we are going to take the distance of one wave is considered to be 1 lambda, because it is traveling in the form of a wave, isn't it? And the time taken is taken as t. Now how will you write the equation? Now we said that the lambda is the distance traveled by the wave and t is the time period of one wave, isn't it? Now how will you write? V is equal to lambda by t. So this is the distance, right? And this is the time taken, right? Now we also know that the frequency, that is n, is equal to 1 divided by capital T, right? Now how will I substitute? Now this can also be written as lambda into 1 by t, isn't it? So instead of this 1 by t, I'll substitute n. So what will be the equation? V is equal to n lambda. So V is equal to n lambda is the velocity of the sound, right? So this equation gives you the velocity of the sound. If you see the velocity of the sound, it is maximum in the solid because they are more elastic in nature compared to that of the liquids and the gases, and this gives you the relationship of the velocity of the sound. If you see, the velocity of the sound is maximum in the solid and it is least in the gas. Now here you can see the tabular column which gives you the speed of the sound in different medium. We said that the velocity of the sound is maximum in the solid and it is minimum in the gas, isn't it? Now here you can see the speed of the sound. For example, copper, iron, aluminium, right? So this consists of an high speed, isn't it? The speed of the sound is high in this solid medium. And if you see kerosene, water and seawater, compared to the solids, it is quite less. And if you see the air at 0 degrees C and air at 20 degrees C, it is very least. So it is minimum in the gaseous medium and it is maximum in the solid medium. Now if you see the factors affecting the velocity of the sound, now in the case of solid, we can say that the speed of the sound is directly proportional to the elastic module. Now how elastic the medium is, and inversely proportional to the square root of the density. Now if you see the density of the solid, liquid and gas, solid is more denser, isn't it? Now the density of the solid is more compared to that of the liquid and the gaseous state. So the velocity of the sound decreases as the density increases. Now whereas the velocity of the sound increases when the elasticity of the medium increases, isn't it? Now if you see the density, the velocity of the sound, especially in gas, we are going to deal only with the gaseous medium. So we are going to find the velocity of the sound the effect of the velocity of the sound in the gaseous medium. So the velocity of the sound in the gaseous medium, if you see, it is inversely proportional to the square root of the density of the gas. So the velocity will decrease as the density of the gas increases, because it is inversely proportional. This density is in the denominator. So as density increases, the velocity of the sound decreases, because they are inversely proportional. The velocity with respect to temperature, the velocity of the sound is directly proportional to the square root of its temperature. When the temperature increases, the velocity of the sound increases. Now this is the formula equation for the velocity at the temperature T. Now here you can see the formula of the velocity at temperature T. Now here V0 is nothing but the velocity of the sound in air at 0 degree C, and V0 will be 331 meter per second, right? And if you talk about the humidity, the effect of humidity, when the humidity increases, the speed of the sound increases. So that's why in rainy season we are able to hear the voice more clearly, because the humidity increases and the speed of the sound increases. Now we'll move to what is reflection of a sound. Now if you talk in an empty room, there will be a small or soft repetition of your voice, isn't it? So this is nothing but the reflection of the sound. So when the sound waves travels in a particular medium, what will happen? It will strike the surface of any other medium, like solid medium. Now if it is traveling through an air medium, now it comes and contact or strikes the surface of the wall, so that is in another medium, isn't it? So what will happen when it strikes? It bounces back, it reflects back. So that phenomena is known as reflection. Now if you see reflection, it is similar to that of the reflection of the light. So the bouncing of the sound waves from the interface between the two medium is called as reflection of the sound. Between the two medium, right? When it comes in contact with another medium, it reflects, it bounces, isn't it? So that is called as reflection of sound. Now the wave that strikes the interface is termed as an incident wave, right? We know that the wave comes from the source and strikes the other medium, isn't it? So that is called as the incident ray. And the other one, the bouncing back wave, is called as the reflected wave, right? Now here in the picture you can see that this is the original wave, so it is called as the incident wave, right? It travels through an air medium and strikes the solid surface, isn't it? So this is a solid medium. Now after it touches the interface of the other medium, what will happen? It gets reflected, isn't it? So this is the reflected ray, and when you draw a perpendicular line between these two, it's called as the normal. And this is the angle of reflection, that is the angle between the incident ray and the normal, and this is called as angle of reflection, the angle between the reflected ray and the normal. Now if you see the laws of reflection, now it is similar to that of the reflection of light. So the incident wave, normal, and the reflecting surfaces will all lie in an same plane. And one more thing is that the angle of incident is equal to the angle of reflection. So these are the two laws that we saw in case of a light wave, isn't it? So similarly here, the incident ray, normal to the reflecting surface, and the reflected wave at the point of incidence lie in the same plane. And what is the other law? The angle of incident is equal to the angle of reflection. So these are the laws of reflection. Now let's see the reflection at the boundary of the denser medium. Now here in the picture you can see the incident waves, isn't it? Now this is the incident wave, and here you can identify the refraction and that is the compression and the rarefaction. Now here this is the compression and this is the rarefaction. Again compression and rarefaction. So alternative compression and rarefaction can be seen. Now if you see this wave, now here it is also given in the wave form. Now here you can see the green part to be the compression and the orange part is rarefaction. So in order to identify the waves, it is given in different colors. Now here you can see that the incident wave starts with the compression, right? Now when it propagates towards a solid medium, so this is the rigid medium, isn't it? Now here this is the rigid medium, so the wave is traveling in the air medium. So when it reaches the interface, now this is the interface, isn't it? Now when it touches the interface, now what will happen here? Also compression takes place, right? Now when it touches the wall, what will happen? It will also exert a force, isn't it? Equal force. Now if the compression wave is exerting a force F on the wall also exerts the same force in the opposite direction, that we have learnt in Newton's third law of motion. Every action has an equal and opposite reaction, isn't it? Now here R, that is the reaction, will be minus F, because the reaction and the force that is exerted will be of same magnitude, but it will be in the opposite direction. So here what will happen? Again, the reflected ray after touching the interface, now what will happen? It bounces back, isn't it? Now even when it bounces back, now here also it starts with the compression, right? So since the compression exerts a force F on the rigid wall, so wall also exerts an equal opposite force, so R will be equal to minus F. So the incident ray and the reflected ray will be the same, but the direction of the compression will be reversed, so, right? So this is about the reflection of the sound at the denser medium. Next we are going to see the reflection at the boundary of a rare medium. Now here you can see the wall, isn't it? So this is a rarer medium, and the wave in which it is traveling in a straight line is a denser medium. So the wave travels from a denser medium and hits the rarer medium. Alright. Now what will happen in this case? Now here also you can see that the incident ray starts from the compression, and here also at the interface it is compression, right? Now this is about the incident ray. Now when the rarer medium is placed at the interface, now what will happen? This compression will exert a force F, isn't it? Now we said that this is the rarer medium and here is the compression, so it exerts a force on the rarer medium. So the compression exerts a force on the rarer medium. Now as the rarer medium has less resistance, now what will happen? The surface of the separation is pushed back, isn't it? So it moves inside. Now since it is a rarer medium, what will happen? It moves inside, it moves in the direction of the incident ray. So what will happen? As the particles in the rarer medium are free, because rarer medium there will be less number of particles, and it is free to move, isn't it? So a rarefaction is created when it bounces back, right? So when it bounces back, now what? So the compression is reflected as a rarefaction, and this rarefaction travels as in reflected ray from right to the left. Now once again I'll repeat, children. Here the incident ray travels from the compression and it meets the interface, that is the rarer medium. Now here the rarer medium consists of less particles, isn't it? Now since it consists of less particles, the particles are free to move, isn't it? So what will happen? This rarer medium will move in the direction of the incident ray. So when it moves in the direction of the incident ray, it is pushed back, isn't it? So this compression will become rarefaction in the reflected ray, and it reflects from right to the left. So the compression is reflected as rarefaction, and the rarefaction travels from right to left. So this is about the reflection of sound at the rarer medium. Now let's see the reflection of the sound in plane and curved surface. Now so far we have seen the reflection at the denser boundary, whether the boundary is a rarer boundary or the denser boundary. Now here whether the surface is the curved surface or the plane surface. Now if it is in plane surface, it will follow the law of reflection, and and the reflected wave will travel in a direction according to the law of reflection. Now if you see, the intensity of the reflected ray is neither decreased or nor it is increased, because it will follow the law of reflection. Now when the sound waves are reflected from a curved surface like this, now the intensity of the reflected ray is changed, right? Now for example, if you see an reflection from a convex surface, now here you can see an convex surface, isn't it? So when the sound waves meets the convex surface, it will get diverged, right? It will diverge out and the intensity will decrease. Now if it is an concave surface, what will happen? It will focus at a point, right? Now after reflection, it is focused at the point, so the intensity of the sound will be concentrated at a particular point and the intensity will be maximum. So parabolic surface are used, it focus at a particular point, at that particular point the intensity will be very high. So the halls are designed in a parabolic reflective surfaces, so that the intensity is more. Here you can see an elliptical surface, isn't it? So in elliptical surface, what happens? The sound that is produced at one particular point, one particular focus, will reflect from the other focus, so it will strikes the wall, so there will be a multiple reflection, you can see. So due to this multiple reflection, now what will happen? Even a small whisper can result in a louder voice. So this principle is used in designing and whispering halls. So in whispering halls, the speech of the person that is standing at one particular point can be heard by a large number of audience who is standing at the other point or the other focus. So this is the whispering hall, you can see in the picture. So this is due to the multiple reflection. So if it is a plane surface, it will follow the law of reflection and there will be no change in the intensity. If it is a convex surface, the reflected ray will diverge out and the intensity decreases. If it is a concave surface, it is focused at that particular point and the intensity will be more or concentrated at that particular point. So the halls, concerts, malls and the whispering galleries are made in an elliptical way, so that the intensity is more. And if the whispering is done in one focus, it can be clearly visible, or it is clearly heard by the audience and the other focus. So this is about the reflection of sound in plane and curved surfaces. So far in this session, we have learnt about how does that sound travel. Now what is the propagation of the sound, and what is the relationship between the speed of the sound, velocity and the time period. And we have also learnt about the reflection of the sound, isn't it? And the reflection at the boundary of a denser medium and the boundary of a rarer medium, and the reflection of a sound in plane and curved surfaces, isn't it? Now in the next class, we will learn about echo and the Doppler effect and numerical problems based on this. Now your homework for today is that now in page number 72, you have answer in detail. So your homework for today is the question number 1. That is, what are the factors that affects the speed of the sound in gases? Now we said the effect of density, effect of temperature and effect of relative humidity, isn't it? So this is the answer. For answer, you can refer page number 61. Prepare the answer for it and write it in the classwork. I'll send you the PDF by tomorrow, and for seeing the PDF also, you can write the answer. Copy this question in the classwork and submit the classwork on Friday in the school office. And we'll meet you in the next session and continue this lesson in the next session. Thank you, children.